My name is Allison Widener, and this is the final report for my project on the optimization of a PA-30 Piper Twin Comanche aircraft's flight altitude. There are many costs associated with owning, operating, and maintaining any aircraft, meaning it can be beneficial to identify cost-saving solutions which don't sacrifice on safety. The Piper Twin Comanche burns about 17 gallons per hour, which at current fuel prices comes out to about $80 per flight hour. This means identifying ways to improve fuel efficiency can result in invaluable cost savings. There are existing programs available to pilots which help them to identify the most efficient operating conditions. However, a lot of these tools leave out important aircraft performance data. Software available to commercial airlines differs from what's available to private pilots. The two are similar in that they both utilize flight plan and weather information for finding the most efficient flighting conditions. However, commercial airline programs utilize actual aircraft performance data, whereas the private pilot tools rely on the inputs from the pilot, which are assumed to be constant throughout all stages of flight. The problem with this is the aircraft performance varies with altitude, so by assuming constant aircraft performance, the most efficient altitude given by the program may not be the most accurate. The objective of my project was to determine which flight altitude resulted in minimum fuel burn for a given travel distance. The assumptions I made were that the temperature and pressure was standard, that there was no wind, the aircraft weight remained constant at 3,725 pounds, which is the maximum gross weight of this aircraft. The climb speed was fixed at 130 miles per hour, the rate of descent was constant at 500 feet per minute, and the power setting in cruise was 65%. In order to obtain the aircraft performance data needed to solve this problem, I referenced the PA-30 Pilot's Operating Handbook, or POH, which contains various charts similar to the one shown here on the left. I then evaluated these charts at each altitude of interest and recorded the data as shown here in the table on the right. These analyses were performed for rate of climb, aircraft speed, and fuel burn. The equation needing to be minimized is the sum of the fuel burn in climb, cruise, and descent. After expanding this equation, it becomes a function of the distance, velocity, fuel burn rates, and altitude. The altitude, which ranged from 3,000 feet, the assumed minimum safe flying altitude, to 16,000 feet, the aircraft ceiling, is the only design variable. Since all the other values of this equation are dependent on the altitude, a piecewise genetic algorithm was implemented into MATLAB, which is a heuristic approach. In order to better illustrate the importance of considering variable aircraft performance rather than constant aircraft performance, 3 different travel distances were considered. As expected, the optimum altitude increased as the travel distance increased. This is due to the fact that climb has the highest fuel burn rates, but higher altitudes have less drag, which results in lower fuel burn rates. So by traveling a longer distance, the aircraft is able to stay at more efficient altitudes longer to help make up for the extra fuel burned in climb. Eventually, I'd like to incorporate wind data, as this is an important factor when trying to find the optimum altitude. In order to achieve the most accurate results, the aircraft performance equation should be used. However, this is typically proprietary information owned by the aircraft manufacturer, so it's unlikely that they could ever be implemented into this specific program.